Okay. And it's Valentine's Day this weekend. You get a long weekend with your Valentine or whoever is special in your life. Okay, let's talk about the binomial distribution. Okay, so we've talked about the normal distribution. I hope we're feeling comfortable with the normal distribution. Tomorrow you will have a quiz that covers the normal distribution and the binomial distribution. So I'm covering the binomial distribution today. I hope it all makes sense, and you have a few problems in your textbook covering this. Okay. All right. So this is how the binomial distribution works. Okay. It's a discrete distribution. Okay. All right. It's a distribution of a random variable, meaning it's a random outcome that that's recorded as a number. And in the case of the binomial distributions, our outcomes are all whole numbers. Okay. Our whole numbers. Is 0 a whole number? Well, whole numbers plus including 0. 0 is an integer. What's the difference between whole numbers and integers? Do we know? Negative numbers can't be whole numbers? Is that true? I don't remember all of these definitions from back in the day. Okay, so and it applies into a situation where so this is the situation where we use a binomial situation for using binomial distribution. Okay, you have a fixed number of repeated trials. Okay, and that fixed number is n. Okay, each trial has 2 possible outcomes. Okay, we arbitrarily label these success and failure, but anything where you can set it up as having 2 possible outcomes, which is everything, can be binomial. Okay, so if we're talking about gender, okay, we can say, so you have to dichotomize everything so that it's either yes or no. So we can say, is someone female? Yes or no. Okay, so we arbitrarily label one of those outcomes. So if we can say female as success, not female as failure. Okay, and that not to say that there's any positive or negative connotation with this, just we label one as yes and one as no. Okay, now we could say we're going to simplify the world, and so it will either be female or not female, and when we say not female, that means male. That maybe that's a simplified view of the world, and we can do that. So if we're talking about someone's hair color, we can say, is this person's hair color black? Yes or no. Okay, so you might have a categorical variable with multiple outcomes, but with the binomial distribution, it's either a yes or a no. Okay, success or a failure. So it could be, we flipped a coin. Did it land heads? Yes or no? Okay. And if it did not land heads, that means it landed tails. Okay. So each trial has 2 possible outcomes. Okay. The probability of success is the same for every trial. Okay, and that probability is P. Okay, and then the trials are independent from each other. Okay, and independent, what does independent mean? It means the outcome of one has no influence on the outcome of another. Okay? All right, so our classic binomial distribution example. Oh, I'm sorry. I'm leaving off an entire thing. Okay. Situation for binomial trials are independent of each other. Okay, and then the value we are interested in is the probability of a certain number of successes. Okay, so we are interested in the probability of X successes. Okay, and it's just the number of successes. The order of successes does not matter. Okay, so we're interested in the probability of just the number X of successes. Okay, so here's our classic binomial distribution example. Okay. I will flip a coin 8 times. Okay, and I'm going to ask, what is the probability that the coin lands heads 5 times? Okay, and I guess, and we can say it's a fair coin. So probability of heads is equal to 0.5. Okay, so in this problem, let's just make sure that the situation for binomial distribution applies. Okay, a fixed number of repeated trials. Yes, we're flipping a coin 8 times. So we can say n is equal to 8. Each trial has 2 possible outcomes, okay? So here the question is, what is the probability that the coin lands heads? So every trial has only 2 possible outcomes. It either landed heads or it did not land heads, okay? And that encompasses everything, every situation where it did not land heads, okay? So that checks out. The probability of success is the same for every trial. Yes, okay, every time we flip the coin, it has a probability of 0.5 of landing heads. So P is 0.5, okay? The trials are independent of each other. Yes, that's how coin flips work. And we are interested in the probability of X successes. So in our case, we want to know what's the probability that we get X equal to 5 heads out of 8. 8 flips. Okay, is that okay? Okay, if I had changed the question to say, what's the probability that the first 2 flips are heads, the next 2 flips are tails, the next 3 flips are heads, and the last flip is tails, is that a binomial problem? No, it's not a binomial problem, because in that case, the order matters, and that just becomes a regular old probability problem. We have to do probability of heads times the probability of heads times the probability of tails times tails on the 4th times tails on the 5th, or whatever, times, I forget what I said, but whatever, okay? So, in that case, the order matters. Is that okay? All right, so let's investigate how we can go about answering this. And so I'm going to just start off with a simpler example, okay? And we're going to say there is, this is a giant bowl of candy, all right? And we got little pieces of candy in here. And you have some strange thing going on where you only like the red pieces of candy. But you're going to pick candies out of the bowl, okay? So we're going to say, so this is a large bowl of candy. We will say 30% of the candies are red. Okay, and we will draw pieces of candy at random. Okay, and we will assume that the bowl is big enough, or that, you know, even after you draw one piece of candy, there's still a 30% chance of getting a candy on the next one, right? So if you had a small thing of candy, that's not the case, right? If you only had like 7 blue pieces and 3 red pieces, you know, as soon as you draw one piece of candy, you know, now you have 7 blue and 2 red, okay? But we're gonna say this bowl is so big that every time you draw, we can just treat it as if there's a 30% chance of getting red each time, okay? Bowl is so big that each draw can be treated as independent and probability of getting red remains the same. The other way we could make sure that the probability of getting red remains the same would be to draw a piece of candy and then put it back in, right? And then mix it up. And that will make sure everything stays the same. So that can be done even with the small. If you only have, you know, 7 blue pieces and 3 red pieces, you know, if you draw one and then you put it back and then shake it, then every time you draw, you'll have a 30% chance of getting red. So that's the other way we can do this. Okay, so we will. So we'll start it off simple, and we will say we will draw 4 pieces of candy. Okay, what is the probability that I end up with 2 red pieces? Okay, and if I get 2 red pieces, that means I also have how many non-red pieces? Okay, so 2 red pieces, and that implies 2 non-red pieces. Okay, so let's just start off with one way we can get 4 pieces of candy. So I'm going to just say red. We're going to call R. Okay, so one possible sequence is to get red, red, and then I'm going to say non-red, non-red. Okay? All right, what's the associated probability? Okay? Well, the probability is going to be equal to the probability of getting red on the first. What's that? 0.3, right? Okay? And then I have to get red on the first, red on the second, non-red on the third, and non-red on the fourth. And these are all independent of each other, so it's going to be 0.3 times 0.3. What's the probability of getting a non-red piece? 0.7, right? Or, 1 minus 0.3. And then non-red on the fourth is also 0.7. Okay? So this probability ends up being 0.3 squared times 0.7 squared. Is that okay? So it's the probability of getting a red one 2 times and a probability of getting non-red 2 times. That's okay? All right. What's another possible sequence for getting red, 2 red and non-red? Okay. Well, I can get red, non-red, red, non-red. Okay. All right, and so the probability of this sequence is going to be 0.3 times 0.7 times 0.3 times 0.7. All right. Well, what do we know? Okay, this probability ends up being, if I combine the like terms, will be 0.3 squared times 0.7 squared. Is that okay? So red, red, non-red, non-red has the same probability of going red, non, okay? And then, you know, I can come up with other sequences. What are the other possible ones? I think I'm doing this correctly. Okay, so these are all other ways to get red, 2 red and 2 non-red out of a sequence of 4. Okay, is that okay? And I hope it's okay for me to then say each of these, each will have a probability of 0.3 squared times 0.7 squared. Okay. So we have 6 possible arrangements, and every single one of these have 2 red pieces and 2 non-red pieces, which is going to be 0.3 times 0.3 times 0.7 times 0.7, perhaps arranged in a different order, like here, 0.3, 0.7, 0.3, 0.7. They might be arranged in a different order, but because multiplication is commutative and the order doesn't matter there, we can just say everyone has 2 0.3s and 2 0.7. So it's 0.3 squared times 0.7 squared. I just want to pause for a second and just make sure everybody can see this. Okay. So because I've got 6 different arrangements, the total probability that I get 2 red pieces if I draw 4 pieces of candy is going to be, so this total probability is just going to be this thing multiplied by 6. I've got 6 possible arrangements, and each arrangement has a probability of 0.3 squared times 0.7 squared. Is that okay? All right, then let's try a problem out. Okay. So we're gonna have the same situation. We've got the vat of candy. Okay, and we'll say 30% are red. Okay, we will draw 4 pieces of candy at random. Okay, and I'm going to ask, what is the probability that I end up with 1 red piece of candy? Okay, which implies a certain number of non-red pieces, right? Okay, so our answer choices. So I'll turn the clicker machine on in a second here. Okay, so we're gonna have so try this out. Let me get iClicker going here. Sorry. How does this? Where did it go? Where did it go? Okay, so people. Oh. Oh, I don't have the right answer available. I'm so sorry. Well, I wonder which one's the correct answer now. I just had to send out this email to my other class because I made a mistake. Like, they had a take-home final or take-home midterm, and I made a mistake, and I was like, oh god. So life is hard. All right, well, who still clicked the other answer choice? Okay, well, one of you. Okay, well, the correct answer is E. All right. So we need to have one red piece, right? One red, which means we have 3 non-red. Okay? So if we just take the first sequence where we just put all the reds in the front, it's going to be 0.3 basically to the first power times 0.7 raised to the third power, okay? But this is for this is the probability for the sequence red, non-red, 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 okay? But we know that there's other sequences, okay? And so what are those other sequences? Well, we've got so these are the other possible sequences, all right? So we have a total of 4 arrangements, and so this is the correct answer, okay? All right, so E is the correct answer choice here. Okay, well, I'm glad somebody caught that. That would have been embarrassing. All right. Okay, are we feeling okay about this? Okay. All right, so all I'm going to do now is just going to put exactly what we have seen here into a generalized form, okay? So keep in mind the symbol that we represent for the probability for one outcome is P, the number of trials that we're doing is N, and the number of outcomes that we want is X, okay? So we've got N, P, and X. Those are the 3 pieces, 3 numbers that we need to come up here, right? So this is 0.3. Okay, so the generalized formula for the binomial distribution is going to be this. If I can flip to the next slide, okay. So formula for binomial distribution, okay. Okay, so we have N trials, P probability of success, and we want X successes, okay? So what it's going to be is we take that probability P and we raise it to the n power. Okay? And then we multiply it by the probability of a failure, which is going to be 1 minus p, right? So in the previous problem we said the probability of getting a red candy was 0.3, which meant the probability of a non-red candy was 0.7. Okay? Now I'm sorry, it's not n. What am I doing here? Gosh, I'm not on my game today here. Okay, we want x successes. Okay, so if we've picked 4 pieces of candy and we want two red ones, that means the number of non-red candies is going to be n minus x. Okay, so it's basically probability of success raised to the number of successes times probability of a failure raised to the number of failures. Okay, and then we have to put a number in front, which is possible arrangements. Okay, so I'm going to put that here, and that's going to be number of possible arrangements. Okay, and that quantity is written as this. This is a funny thing. It's also called n choose x. Okay, n choose x. This basically is the number of possible arrangements. Okay, so n choose x is basically saying with n trials, how many ways can I arrange x successes? Okay. There is a formula for it. N choose x is this. I don't expect you guys to memorize this, but I'll put this out here for completeness. Okay, and this is an exclamation point indicating factorial. So it's n factorial divided by x factorial times n minus x factorial in the denominator there. I don't expect you guys to really make use of this. Really, on your calculator, you probably have a choose button. On the calculator, there's probably a NCR function somewhere on there. So on my calculator, it's above the division sign, okay? It says NCR. If you've got a Texas Instruments calculator, you might have to hit the math button or the PRB button, or you go on math and then go through the menu for PRB. And then one of your options should be NCR, okay? And so, you can test this out and you can say, well, if I have four trials and I want 2 successes, how many ways can I arrange that? Well, we saw that there were 6 possible arrangements, right? So 4 choose 2, if I hit enter, will give me 6. So on your calculator, maybe you have to hit the math button or the PRB button and use your arrows to get NCR, and you should be able to do 4 NCR2, and that should give you 6. Okay. If you have a different calculator and you can't find it, no worries. Okay. So we can ask things like, if I'm going to flip the coin 10 times and I want 5 heads, what would I choose? Or what would I enter? 10 coins, 5 heads. How many arrangements? I would do 10 choose 5, right? So I would do 10, and then on my calculator I hit choose 5, and it says there's 252 ways to arrange 10 flips, so there's 5 heads, okay? 252 ways. And all of those arrangements are going to have the exact same probabilities. Okay? They'll all be p raised to the x, 1 minus p raised to the n minus x. Okay? Is this so far okay? All right, so you know, let's say we do this, okay? So we'll say 10 coin flips, and you know, probability of heads is equal to 0.5. What is the probability I get 5 heads? Okay, again, order doesn't matter in this question. Okay, so our answer is going to be number of ways to arrange 5 heads times probability of heads raised to, you know, 5 heads times probability of tails raised to the basically number of tails. So this is going to be 10 choose 5 times probability of heads is 0.5, and I want 5 of them. Okay, what's the probability of getting tails? Also 0.5, or 1 minus 0.5. Okay, and how many tails do I need? I will also need 5 tails. Okay, so this ends up being 252 times 0.5 raised to the 5 times 0.5 raised to the 5, which ends up being 0.5 raised to the 10. So I can just do 10 choose 5 times 0.5 raised to the 5 times, whoops, oh no. How do I, there we go, times 0.5 raised to the 5, okay? That's not helpful. 0.246093. Okay, so if you flip a coin 10 times, you've got about a 1 in 4 chance of getting 5 heads. Are we feeling okay with this? Yeah? Okay, let's make our life harder then. Not really. Okay. We can talk about all of the possible outcomes, right? So let's say we go back to our candy bowl with 30% red. Okay, and then we're drawing 4. Okay, what are all the possible outcomes for the number of red pieces I get? Okay, well, the number of red pieces I can get, so I'm going to say x as the possible outcomes. I can get anywhere from 0, 1, 2, 3, or 4, okay? And we can find the probability of each of these things, okay? What's the probability that I end up getting 0, okay? Well, this is going to be what? 4 choose 0, 0.3 raised to the 0, and 0.7 raised to the 4, yeah? Okay, and then all of these, you know, they just follow a similar pattern. 4 choose 1, 0.3 raised to the 1, 0.7 raised to the 3. I'm going to just go ahead and fill this out. Okay, and so we can calculate all of these values here, okay? Somebody could ask, what is the mean mean of, or I guess, yeah, the mean number of red candies we expect. Okay. So if we were to repeatedly play this game where I'm drawing 4 pieces of candy out of the bowl, you know, sometimes I would get 0 red candies, sometimes I would get 1, sometimes I would get 2, so on and so forth. If I did this thousands or millions of times and I kept track of every single outcome, what do you think my mean is going to be? Okay, well, I think it makes sense. The mean is just n times p, which is going to be 4 times 0.3. So on average, I would get 1.2 red pieces of candy. Now, of course, on any individual trial, I'm not going to get 1.2 red pieces of candy. I'm either going to get 1, or I'm going to get 2, or some whole number. But if I kept track of every single one of these outcomes, and I took the average of all of them, that average, that mean, would be n times p. So our mean number of, the mean number of successes is going to be n times p. All right? And I think that makes intuitive sense. The standard deviation of our outcomes, so if I kept track of all of our outcomes, and I took the standard deviation of all of them, that standard deviation is going to be n times p times 1 minus p, and then I take the square root of all of those values. Okay, so in our example, we would have the square root of 4 times 0.3 times 0.7. And I would take the square root of this thing, which is 0.9165. Okay, and so this is, again, the idea is if I kept track of all of my outcomes after many repeated trials, what is the mean of all of those outcomes? What is the standard deviation of all of those outcomes? Okay. All right, and then so here's the last part. What if I asked a question such as, what is the probability that I get more than 1 red candy? Okay, so here's the key phrase: more than 1 red candy. Okay, well, more than 1 red candy means I need 2, 3, or 4 pieces of red candy. Okay, and so here I have 2 ways to solve this. I can go, I can find the probability of 2, find the probability of 3, find the probability of 4, and add all of those together. The other option is I can do 1 minus the probability of 0 or 1. Okay, so I'm going to write 2 ways to solve. Okay, so we have the direct, which is going to be probability that x is 2 plus the probability that x is 3 red candies, plus the probability that x is 4, that I get 4 red candies. Okay, so this is one way to answer the question: what's the probability that I get more than 1 red candy? I add up these 3 numbers. Okay, that's the direct way. The other way is the complementary way, right? And for the complement, I would do 1 minus, and I would add up these 2 numbers: probability of getting no red candies or the probability of getting 1 red candy. Okay. And so the idea is I can either add up these 3 numbers, okay, the outcomes of these 3 answers, or I can add up these 2 numbers and subtract this quantity away from 1. And then I know, because I know everything, all of the outcomes added together add up to 1. And I hope we can see that. Okay, so we'll do, this will lead us to our final, I guess just our last clicker question. So if I may flip the slide, okay. All right, so I can say, how can I answer the question? What is the probability of getting more than 2 successes? Okay. All right, so your answer choices are sorry, this last one is just going to be probability that x equals 3. And we'll say 10 trials. And okay, so we'll run that. Okay, I'm gonna hit stop there. Looks like most of you got it here, okay? And the answer choice is indeed C. So again, when it says more than 2 successes, I can add up all of the probabilities 3 through 10, but that would be a lot of numbers to add up. The other option is to just find the probability of 0, 1, and 2, add up those 3 numbers, and subtract that from 1, okay? All right, so you guys have a little bit of practice in your homework, and this stuff, you will see it on tomorrow's quiz and section, okay? All right, have a good night, you guys.